In this video, we're going to be looking at the use of hexadecimal to represent binary. All right, so to motivate why we do this, take a look at this 32-bit sequence of binary digits. Look at that for about 15-20 seconds and then try to write it down on a piece of paper without looking back at it. It's very difficult to do and it's very error prone. So if we were able to convert this to an easier representation, and that's what we do when we use hex. In hex, this would be B5C2A94F. All right, you could look at that for 15-20 seconds and you'd have a much better chance of copying that down correctly on a piece of paper. All right, so that's one aspect of this. It's hard for human beings to look at binary and see what we need to see with any level of precision and accuracy. Another thing, let me show you this demonstration. Look at this sequence, all right? They only differ by 1 bit. It's pretty hard to see it. Unless you move to hex, this is the hex representation, the difference comes between 3 and 7. So only 1 bit difference, but you have to look. Oh, there's that other bit that got flipped between those two sequences. All right, so it's just a convenience to look at things in hex, all right? Now, I just said the word hex, and it actually is a little bit wrong because hex would imply base 6, but hexadecimal, you take the 6 and you add the 10, that's base 16. You actually need it to be base 16, but the common abbreviation for saying that is to represent this in hex. So basically what you do with hex is you take groups of 4 bits, all right, because we have 4 bits, the range is 0 through 15. All right, and then we assign the decimal numbers in the natural way. So for example, 2, 0, 0, 1, 0. If I convert that to binary, I get decimal 2. 9, 8 plus 1 is 9. Okay, so those are those digits. And then we add on extra digits. And because we run out of symbol names, we need to label what 10 would be. So 10 is A, 11 is B. 12 in decimal is C, 13 D, 14 E, and 15 F. And these are the corresponding bit patterns, and these fit naturally because this is the binary representation of those decimal numbers. Okay, so you now know how to convert hex. It's really pretty simple. The thing that you need to think about, though, is typically on a piece of hardware, we have a certain number of bits in mind. So in this particular case, I've started with 8 bits. And if I do 1, 0, 1, 1, I can convert that. I would get 8 plus 3, which is 11. 11 would be B, all right? So what if I flipped a bit here? Oh, if it's all ones, that would be F. If I turn these back off, that's 9. So you see how that goes. It's just a matter of doing the binary equivalent to show up with the hex representation. And of course, it goes in both directions. I could put A here, and 1, 0, 1, 0, 8 plus 2 is 10, okay? And so that's a pretty straightforward process. But we could also expand this to be, to represent wider bit fields. So let's say I had 10 bits, all right? With 10 bits, I can pad the most significant bits, and these would always be zeros if I'm doing unsigned numbers, okay? And so then, the most I would have here is 3. I can't get any bigger than a 3 because these other 2 bits are not used. All right, so you see that's the kind of nuance if you don't have a multiple of 4. So if I keep adding up to 12, I'm back to multiples of 4 and I get the full range of that upper most significant digit. All right, so that's the basics of hex and conversion between binary and hexadecimal. I think it's pretty easy to go back and forth. That's the whole point. Don't overcomplicate this. It's really easy to do binary to hex and hex to binary.